software testing methodologies, public question paper, video 3, that is Unit 3, public questions. Unit 3, public questions are important questions. So most important questions is compare and contrast nice and ugly domains. What is nice domain? The representation of nice two-dimensional domains is shown in the following figure. This one. Now here U and V represents boundary sets and D represents domains. The boundaries have different important properties. They are linear, non-linear, complete and incomplete, systematic, orthogonal, consistently closed, convex and simply connected. If domains have these properties, domain testing is very easy. Otherwise, domain testing is very difficult. The different properties are linear and non-linear boundaries. Nice domain boundaries are defined by linear inequalities or equations. If the test comes from 2 points, then it represents a straight line. If it considers 3 points, then it represents a plane, and in general, it considers n plus 1 points, then it represents an n-dimensional hyperplane. Linear boundaries are more frequently used than the non-linear boundaries. We can linearize the non-linear boundaries by using simple transformations. Second one, complete and incomplete boundaries. If the boundaries do not have any gap between them, then they are called complete boundaries. If the boundaries have any gap between them, then they are called incomplete boundaries. Incomplete boundaries. This one. Here, if the gap is there, then it is called as incomplete boundaries. If there is no gap, then it is called as a complete boundary. So the boundaries A and E both have gaps, so they called as incomplete boundaries. And the boundaries B, C, D have no gaps, so they called as a complete boundaries. Systematic boundaries. Systematic boundaries represent two boundary inequalities. For example, f1x greater than or equal to k1 or f1x greater than or equal to g1c. f2x greater than or equal to k2, f2x greater than or equal to g2c, and so on. Fix greater than or equal to ki or fix greater than or equal to gic, where fi is an arbitrary linear function and x is the input vector, ki and c are constants, and gic is a decent function that gives a constant such as k plus ic. Orthogonal boundaries. If we tilt the u and v boundary in nice domain, we can get the following figure. This figure, the following figure, we will get it. The following figure will get it. The u and v boundaries in nice are orthogonal because every boundary v is perpendicular to every other boundary u. If two boundaries are orthogonal, then they can be tested independently. Here we can do testing by its intersection points, but this can change the linear growth order of n into the quadratic growth order of n square. Only it can change about the linear growth to quadratic growth because of tilting. Closure consistency. Consistent closures are simple and gives consistent and systematic results. The following figure shows the boundary closures which are consistent. In the below figure, the shading lines show one boundary and thick lines show other boundary. It shows non-orthogonal domain boundaries because x is not perpendicular to y. Convex. For any two boundaries with 2 points placed on them are combined by using a single line, then all the points on that line are within the range is called convex. For any two boundaries with the 2 points placed on them are combined by using a single line, then all the points on that line are within that range is called convex. Nice domains support convex property. Simply connected. Nice domains are simply connected because They are available at one place as a whole, but not dispersed in other domains. Nice domains are simply connected because they are available at one place as a whole, but not dispersed in other domains. Mostly, if a domain is convex, then it is simply connected. Ugly domains. Some domains are born ugly are called ugly domains. Some domains are born ugly are called ugly domains. Some domains are bad specification. Every simplification gives either good or bad. The different properties of ugly domains are given by nonlinear boundaries. We don't know how to correct nonlinear boundaries. So if a domain boundary is nonlinear, then make it linear boundary. Ambiguities and contradictions. Ambiguity means see incomplete boundary is called as a ambiguity boundary. Contradiction, dual closure, then contradiction, overlapped domains, then ambiguity, missing boundary. So ambiguity comes under incomplete boundary or missing boundary. Contradictions comes under overlapped domains or dual closure. Ambiguity in domain is missing or incomplete domain boundary. In the above figure, ambiguities are holes, that is incomplete boundary in A domain and missing boundary in B domain. Similarly, an ambiguity for one variable can see easy, but an ambiguity for two variables can be difficult to see. An ambiguity for three or more variables impossible to see, hence tools are required. Contradictions are overlapped domains or dual closure. There are overlapped domain specifications, overlapped closure specifications. In the above figure, there is overlapped domain and there is overlapped dual closure. Contradiction. Simplifying the topology. Connecting disconnected boundary segments and extending boundaries is called simplifying the topology. Connecting disconnected boundary segments and extending boundaries is called simplifying the topology. There are three generic cases of simplifying the topology. Here, making it convex. First one is making it convex. Second one is filling the holes. Third one is joining the pieces. One is making it convex, another one is filling holes, and last one is joining the pieces. Joining the pieces. Rectifying boundary closures. Different boundaries in different directions can obtain in consistent direction is called rectifying boundary closures. Different boundaries in different directions can obtain in consistent direction is called rectifying boundaries. So domain boundaries which are different directions obtain in one direction. So here boundaries are different directions you can obtain in same direction is called consistent direction. Here three are same directions. One is outside direction, so that can make it in inside direction. In the above figure, the boundary is outside, that can be inside. This is called inclusion, exclusion, consistency. Inclusion, exclusion, consistency. First question is for nice and ugly domains. Important question. Okay, important question. First question is completed. Now to go about the second question, explain domains and interface testing. This is also most important question. The domain testing plays a very important role in integration testing. In integration testing, there may be interface of different components. This question also asked in university examination. So the domain testing plays a very important role in integration testing. In integration testing, there may be interface or different components. Domains and range. Domains are the input values used. Range is output obtained. In most testing techniques, there may be more forces on input values, but interface testing gives more forces on the output values. An interface test consists of the following mappings: caller domain, caller range, call domain. Caller domain to caller range, caller unit test. Caller range to call domain, integration test. Call domain to call range, call unit test. Closure compatibility. Assume that the caller's range and call domain spans the same number, say 0 to 17. If the caller and call have same span, then it is called closure compatibility. The closure compatibility shows 4 cases in which the caller range closure and call domain closure can agree. The four cases consist of domains. They are both closed on top and bottom, open top and closed bottom, closed top and open bottom, and open top and bottom. Here thick line represents closed and thin line represents open. The following figure represents range domain closure compatibility. See here, collar called both closed, open top, bottom closed, open bottom, open bottom, open bottom, open top, open bottom, and both opened. The following figure shows the 12 different ways the collars range closure and called domain closure can disagree. Here, not all of them are necessary bugs. So you can see here, this one, how many ways you can write. You can write. The most important question is span incompatibility. If the caller and called have different spans, then it is called span incompatibility. If the caller and called have same span, then it is called span compatibility. In the following figure, caller span is smaller than called span. Here it is not necessarily bugged. See here it is 3719 different, 3919 different, 1719 different. Now, in the following figure, called span is smaller than caller span. Here are all bugs, that is 1937, 1939, 1917. In the following figure, the caller and call mismatch, hence good values are rejected, bad values are accepted here. 1739, 3917. In the following figure, there are holes in the call domain. These are all buggy. Hole here, 351 hole, here 361 hole, here at 7 point there is a small hole. Next, third question, role of path products and path expressions. Role of path products and path expressions. What is meant by the path? A sequence of statements which starts at an entry and ends at an exit and passes all the decisions, junctions, and process is known as path. A path represents different links and we can give a name to the link. The link name will be denoted by lowercase cyclic letters. In traversing a path, we traverse link names that give the name of the path. If we traverse links ABCD, then the name for the path is ABCD. This path name is also called a path product. The following are some examples of paths here given clearly. EACF, EADF, EADF, EBCF, EBCF, and EBDF. Similarly, here the different paths, by seeing these directions, you can say one. So A, B, C, D, E, this is the shortest one. Then A, B, G, K, H, D, E. That is one. Like that, you can write about the different paths. Here the different paths are nothing but AC, ABC, ABBC. So here B is nothing but the self loop. The different paths are here ABD, one direct ABCD, then ABC, BC, BD, then ABC, BC, BC, BD. These nothing but the different paths. Path products, the concatenation of names of two consecutive path segments is called a path product. For example, if X and Y are defined as follows: X equal to ABCD and Y equal to FGHIJ, XY equal to ABCD, FGHIJ, AX equal to ABCD, XAX equal to ABCD, ABCD, YX equal to FGHIJ, ABCD. Then XA equal to A, B, C, D, E, X, and A, small letter A last. Another example is if X equal to ABC plus DEF plus GHI and Y equal to UVZ plus UVW plus Z, then XY means you have to multiply both. Then you get ABC UVW plus DEF UVW plus GHI UVW plus ABC Z plus DEF Z plus GHI Z. If X equal to ABCD, then X power 1 equal to ABCD only. X square equal to ABCD whole square, that is ABCD into ABCD, and so on. The path product is not commutative, that is XY does not necessarily equal to YX. The path product is associative, that is XYZ equal to X into YZ. Path expression. Path expression is defined as an expression which represents set of all possible paths between an entry and exit nodes. Between an entry and exit nodes. Here, how we can write about the path expression here. Here, how we can write about the path expression. F into x plus y plus d, x plus y plus d. F into x plus y plus d, x plus y plus d into g into uvw, u plus v plus w plus h plus I plus j into k. That is nothing but the path expression. The path expression to the above figure is f into, first one is f into x plus y plus d, f into x plus y plus d into g into u plus v plus w plus h plus I plus j into k. Path sum. The path sum is the sum of all parallel links between two nodes or sum of all parallel paths between two nodes. Path sum is denoted by plus. The example is one is given by e into a plus b into c plus d into f. The above figure links A and B are parallel, so these parallel paths are generated by A plus B. Similarly, C and D are parallel. These parallel paths are generated by C plus D. The set of parallel paths between 1 and 2 nodes are EACF plus EADF plus EBCF plus EBDF. Okay, EACF. First one is EACF, EADF, EACF, EACF, EADF. Okay. Generally, how you can write? You can write about E into A plus B into C plus D into F. If you expand your get like this, then the example 2 is given by F into x plus y plus D into G into U plus V plus W plus H plus I plus J into K. The first set of parallel paths is generated by x plus y plus D, and second is u plus v plus w plus h plus I plus j. The set of all paths in this flow graph is f into x plus y plus d into g into u plus v plus w h plus I plus j into k. Path sum is commutative and associative. Commutative is x plus y equal to y plus x. Loops. If a single link or path expression is traversed in infinite number of times, if a single link or path expression is traversed indefinite number of times, leading to infinite number of parallel paths, then it is called loop. For example, the loop consists of a single link B. Then the set of all paths through that loop is b power 0 plus b power 1 plus b square plus b power n up to b0, b1, b2, b3, bn. The infinite sum is denoted by b star. So b star equal to b0 plus b1, b power 1 plus b power square, b2 plus dash dash b power n. If the loop is taken at least once, then it is denoted by b power plus. Example 1, a, b, c. Here the path expression is a, b power star c, because b is nothing but a self loop here. So that is taken by a, b power 0 c plus a, b power 1 c plus a, b square c plus a, b cube c plus dash dash. That is given by ac plus abc plus abbc plus abbc plus dash dash dash. Example 2, a. So first one is a, b, c, d. A, B, C, B, C, D, A, B, C, B, C, B, C, D. Like that it comes. The path expression is A, B, C whole power star B, D. That is A, B, C whole power 0 B, D plus A, B, C power 1 B, D plus A, B, C square B, D. So here B, C whole power 0 comes under the for whole B, C power 0. BC power 1 means whole BC whole power 1. Here BC power 2 means whole BC square BD. So that's why it comes ABD plus ABC BD plus ABC BC BD plus dash dash dash. Okay. So these are the most important questions or previous university examination questions under unit 3. Thank you.